Since we're in the thermochem unit, it's only natural to start talking about heat, which is represented by a lowercase q. We would see that capital H was enthalpy and lowercase h was Planck's constant. So heat is defined as energy transferred as a result of a temperature difference, and that's key. So we're going to see that energy is going to flow from the higher temperature region to the lower one. So when we look at it, we're looking at a warmer object is going to be transferring its heat to the cooler object for it. And we can see this if we sit on our chair in school or if we sit on like a leather couch. It's going to feel cold right when we sit down, but over time, the heat from our bottom is going to transfer into the chair or the couch for it. And then when you get up and you feel the chair or the couch, you're going to feel that it's warm because the heat from yourself has transferred to it. So how do we measure changes in heat? Well, we measure them with a thermometer. It's just a simple instrument for measuring and indicating temperature in Celsius or Fahrenheit. So we have degree C or degree F for it. So what was in the original thermometer? Well, that's actually tricky. Most people are going to say it's mercury, but it was actually alcohol. And we're going to see that Fahrenheit worked with it in 1709 in Germany. Now, it doesn't discount that most people think that thermometers have mercury in it because in 1714 that was the standard for science, was to have these mercury filled thermometers. Up until about 2000, mercury was used for scientific thermometers. Our school even had these thermometers with mercury in it. Now they've been phased out because of the hazards with mercury to use this alcohol based one. So alcohol was actually the first or original thermometer in 1709 with Fahrenheit in Germany. In very cold climates, you'll still see that they use a mercury thermometer because it's more accurate than alcohol for those lower temperatures. So how do we measure heat in Q? Well, we can measure it in all different things like big C calories, little c calories, joules, and kilojoules. Now, calories sound familiar because our food is measured in calories or how much energy it takes for us to burn them off. Now, that's a whole different lesson to focus in on big C versus little c for that and the calories we consume. We're going to focus in more qualitatively than quantitatively. So, if we can measure the amount of energy that's transferred to a system, we know a system's heat capacity. So, if we look at something's capacity is how much it can take on. So, what is the heat capacity of a substance? Well, heat capacity is the amount of heat needed to increase the object's temperature by 1 degree. So if we're looking at heat capacity, it is mass dependent. Depending on the amount of mass you have, changes its heat capacity for it. So which one would heat up faster, a simple nail or a steel bridge? So if we keep that in mind that it's mass dependent, we would see that the nail would heat up faster than the steel bridge for it because it is a smaller amount there. Now, which one would heat up faster, a swimming pool full of water or a wading kiddie pool? We would see that the kiddie pool would heat up faster because there's a smaller amount to it compared to a full Olympic-sized swimming pool. The same thing as if we added the ocean in it compared to a pool. So heat capacity tells us that different substances respond in heat all different ways. If a metal chair sits in the bright sun on a hot day, it becomes quite hot to the touch. An equal mass of water in the same sun will not become nearly as hot. So we would say that the water has a high heat capacity, and this is why they use water as a coolant for machinery. Now, specific heat is literally in its name. So specific heat is looking at a specific mass, whereas heat capacity is not mass dependent. It will be represented by big C. So it's the amount of heat to increase the temperature of 1 gram by 1 degree Celsius. Get it? It's more specific than heat capacity. So we can look at the general specific heats for building materials. So we can look at our materials going here, and then we can look at their specific heats. The higher the specific heat, like water, we'll see it's less affected by heat forward, so it takes more time to heat up. The lower the specific heat, the more affected it is, and that makes sense. If we go out barefoot on asphalt, we know it is very, very hot for there. Same thing with bricks. Concrete, most things that we walk on, if you go to the beach and the sand is unbelievably hot for it, is because that lower specific heat, it's more affected, and we're going to see that it takes in that heat faster than water, which has a high specific heat. So thanks for watching about these thermochem terms.